With approximately 17,000 diagnoses per annum in Australia, prostate cancer is a prevalent health concern for men across the globe. A slow progressive disease, the risk of developing prostate cancer increases with age, though factors such as genetics can contribute to an earlier appearance. The TNM test and Gleason's grade are the primary methods for identification of the stage and severity of prostate cancer. In TNM testing, 3 categories of increasing severity, localized advanced, and metastatic prostate cancer, determine the course for the most effective therapeutic action. Our proposed treatment, Prostaid, intends to combat the first 2 categories of prostate cancer and prevent progression to the final metastatic phase by targeting 3 underlying traits of the disease: metastasis, cellular proliferation, and apoptotic resistance. These traits arise from a class of hallmarks that drive the development of cancer in general.
Our treatment consists of a 2-step process targeting more than one hallmark of cancer. Part 1 of Prostaid involves localizing the tumor and inhibiting the mechanisms involved in tumor metastasis. Within prostate cancer cells, the 26S proteasome constitutively releases inhibitory kappa B from nuclear factor kappa B by degrading it, pushing nuclear factor kappa B into its active state. Additionally, the presence of a protein complex phosphorylates the inhibitory kappa B unit, again activating nuclear factor kappa B. The activated nuclear factor kappa B then translocates to the nucleus, binding to the SNEL promoter region to activate transcription and translation. The newly formed SNEL protein has 3 effects intracellularly. It directly methylates the RKIP region by binding to its promoter region, and upregulates the production of the mesenchymal markers vimentin and fibronectin. These markers signal the cell to undergo phenotypic changes and contribute to the process known as epithelial to mesenchymal transition. Once inside the cell, the drug NPI-0052 irreversibly binds with increased specificity to the 3 functional enzymatic units, caspase-like, trypsin-like, and chymotrypsin-like, for a longer duration than other classical proteasome inhibitors. This inhibition suppresses the degradation of inhibitory kappa B, resulting in inactive nuclear factor complex. This prevents transcription of SNEL markers, allowing the transcription of RKIP. In its active state, RKIP directly binds to the protein complex, keeping the nuclear factor kappa B in its inactive state. The inhibition of the 26S proteasome also suppresses proteasomal degradation of misfolded proteins. As these proteins accumulate in the intracellular matrix, they induce cell toxicity, leading to cell apoptosis through the caspase-8, caspase-3 mediated pathway.
Part 2 of prostate combination therapy involves targeting 2 hallmarks prevalent in prostate cancer: cellular proliferation and apoptotic resistance. The receptor TMEFF2 is selectively expressed in the brain and normal prostate and overexpressed in prostate cancer. The tumor microenvironment stimulates the activity of metalloproteinase, type 2 transmembrane serine proteinase dependent cleavage at specific recently identified sites on TMEFF2. This causes TMEFF2 shedding, giving rise to a non-functional, cytoplasmic, and soluble ectodomain components. The latter fragment binds to an unknown receptor which generates a signal cascade activating AKT. Highly active across low and advanced prostate cancer, AKT triggers apoptotic resistance by driving inactivation of BAD and caspase-9. It also suppresses high ERK-MAPK activity by phosphorylating RAF1 at site serine 259. This ultimately causes expression of E2F, leading to constitutive cellular proliferation. We propose to eliminate this pro-tumorigenic activity by designing and implementing small molecules that combine to and thereby block the cleavage sites on TMEFF2. Furthermore, studies have displayed a tumor suppressor role for TMEFF2. Activated by growth factors EGF and PDGFAA, overexpressed TMEFF2 stimulates high activity of the ERK-MAPK pathway in prostate cancer cells. These conditions favor senescence-associated protein degradation by intracellular proteasomes. Consequently, key promoters of tumorigenesis, such as c, Myc, and STAT3, are degraded, leading to impaired proliferation, growth arrest, and eventual apoptosis.
Presently, considerable work needs to be done to make Prostaid a reality. Of most importance is designing a small molecule drug targeting cleavage sites on TMEFF2, whereby ongoing development in modern modeling techniques in computer-aided drug discovery holds promise. Determining the most effective delivery and duration for treatment stages undertaking animal model trials, and minimizing any negative effects. Our proposal for prostate cancer aims to target 3 dominant hallmarks: metastasis, apoptotic resistance, and cellular proliferation. Prostate is novel and ambitious in nature, with the intention to eradicate the progression of prostate cancer after diagnosis through its two-part application. It is unlike present passive and aggressive therapeutic strategies, such as surgery, chemo, or radiotherapy, which can severely impact a patient's everyday life. Thus, to advance the combat against prostate cancer, please support the creation of Prostate.